presentation by group, okay, on the project. So at first you have to identify the problem and take a case study, and you have to use the advanced analytical model. So try to get the data set and provide detailed solution using deep learning techniques in artificial neural network. Okay, and then you have to provide step by step on how data is analyzed with deep learning. Right? You can use this guide as a process process for the time being, where you can use for your project. Right? And today we will have a project presentation with the project leader
Assalamualaikum warahmatullahi wabarakatuh, and selamat datang di Dr. Burhan. So we are from Group GS21 and we will be presenting our project which is car price prediction system. So first of all, I'll introduce our group members. First we got Muhammad Syahid Ministry, then Muhammad Islam Hisham, then we are Muslim Anwar, and lastly Ahmad Mahmud. So next for our group abstract. Firstly, this project is the development of a car price prediction system utilizing artificial neural networks, which is ANN, to estimate vehicle price based on specification. So basically, this is our objective for our project. Next, the approach involves analyzing such data that includes engine horsepower and prevent to uncover patterns that influence pricing. The data set was manually created to reflect the broad range of car types available in the automotive market. Next, the ANN model implemented using the TensorFlow and price service for trained and optimized through advanced deep learning techniques such as robot regularization, mesh normalization, and conditioning. And lastly, the goal of this prediction system is to support informed decision making for buyers, sellers, and industry analysts analyzed by providing reliable and data-driven price estimates. So next for our introduction to case study. This case study focuses on the development and implementation of neural network model for car prediction analysis. The goal is to design and implement neural network model that can deliver accurate and reliable prediction, thereby supporting data-driven decisions and such as pricing strategy, based on evaluation and market share analysis. This case study outlines the complete workflow from the data processing and model development to training, testing, and simulation, demonstrating how neural networks can be applied effectively to overcome prediction challenges. So next model.
Now we will proceed to Python installation and then deep learning. Which will improve the possible much Python to provide Python detection and have a comprehensive, efficient, and highly optimizable environment for Python development. We have used Python language why artificial neural network. Artificial neural network are powerful choice for car prediction system. They are ability to learn complex patterns and relationships in data, especially when dealing with the highly diverse and often undefined factors that influence automotive scenarios. Explanation on deep learning. What is deep learning? Deep learning is transforming the way machines understand, learn, and interact with complex data. Deep learning uses neural networks of the it enables computers to autonomously uncover patterns and make informed decisions from vast amounts of unstructured data. The five process is deep learning. First, we understand problem and whether deep learning is a good fit. Then, we train algorithm on large amount of table data. Then, we identify the relevant data sets and prepare them for analysis. Then, we test the model performance against unlabeled data. And finally, we choose the type of deep learning algorithm to use. Some of the key concepts in the networks, layers, which is input, hidden, and output, neurons, weights, bias, and attribution functions.
We're going to begin description about our data. So first of all, our data is taken from Kaggle that contains around 11,159 file listings. So this stuff is basically from Malaysia, mostly from Malaysia, and we import the data from Kaggle to Excel. So the key features in the data set: first, make, which is a manufacturer brand, or as well as the car brand, and then model, which is the model of the cars, and then year of manufacture, engine fuel type, which is petrol or diesel, engine HP, engine cylinders, transmission type, which is manual or automatic, and lastly, driven wheels, either four-wheel drive, right-wheel drive, or automatic wheel drive. So the additional features: number of doors, market category, vehicle size, vehicle style, highway MPG or city MPG, which is fuel efficiency, and lastly the popularity, which is the interest or sale-based score.
Hello everyone, today I will be presenting the flowchart and learning process for the car price prediction system. This model combines structured data processing, neural network design, and generative input to create an accurate and scalable pricing tool. So first we will see the workflow overview. The model follows clear and sequential workflow, starting with raw data processing, followed by model development, training, and performance evaluation. Each step is designed to ensure the model is both accurate and practical for real-world development. So next we have the data preparation and training. We begin by loading the dataset. We must source from the internet, and it includes a wide range of vehicle specification. To ensure data reliability, and all rows with missing values were removed. Then we introduce a new feature called car age, calculated by subtracting the vehicle measuring year from the current year, 2025. This gives us a better understanding of the precision trends than the raw year value. After that, we have the target variable transformation to address the SQL distribution and extreme values in the target variable. MSRP, we apply a log transformation using np.log1b. This helps smooth the data, reduce outliers impact, and allow the model to learn more effectively. Then we do the data splitting and pre-processing. The clean data set was split to 80% training and 20% testing. We use the scalar to normalize numerical feature like horsepower and mileage. And one input for categorical features such as make, model, and transmission type. This transmission will wrap in column transformers to streamline the process and avoid data leakage by fitting only on the training side. Next, the deep learning model architecture, which use the Keras Sequential API featuring 3 hidden layers, 512, 256, and 128 neurons. We use ReLU activation for non-linearity and included batch normalization to speed up streamlined training, drop out layers to prevent overfitting, and L2 regularization to analyze large weight. The output layer had a single neuron with linear activation, since we are predicting continuous values. Then we compare the model with the Adam optimizer at a learning rate of 0.005. The loss function must be square error, with mean absolute error as an additional metric for interpretability. To avoid overfitting, we use early stopping, monitor the validation, loss and stop training if improvement was seen after 20 consecutive epoch, while restoring the best weight. Then we do the sub-training behavior and performance. While training, we observe the consistent learning, both learning and validation, loss decrease steadily. Batch normalization and dropout help the model generalize better, not just being memorize the data. The training we validated the model on the dataset and converted prediction back to original prices. Then for the real-time user interface, to make the model user-friendly, we integrated a simple interface that accepts user input like read, knowledge, view type and transmission. Based on this, it detects a real-time estimated market price. This feature demonstrates the model practical value not just as project but as a functional tool for leadership, governance or pricing platforms. Then, after the flowchart learning process, we have the step-by-step learning, analysis and finding. So first we have development approach, structured and iterative process for the data processing and modulation to read the data and then clean the data set. So next we have data cleaning and feature engineering, remove all rows with missing values. Created new feature car age, we use 2025 minus the year of the car. Then we improve data relevance for modeling car depreciation trends. Then we have target for level, which is similar to for applied log transformation. And then outliers, normalize data distribution and stabilize modeling. Then we have data set splitting, which uses 80-20 split ratio for training and testing set. Example is model training with reliable inflation. And then we do data processing strategy, use numerical feature, standardize using standard CLR, categorical feature, one hot encoded, use column transformer for automated consistent transformation, and prevent data leakage by fitting only training data. So for the model architecture, I said before, the current sequential, use 3 hidden layers, 512, 256 and 128 neuron. The technique we use is value activation and batch normalization. We are drop 30% in early layers, 20% in later. L2 regulation for overfitting control, and layer 1 neuron, linear activation for regression. Then we do the training configuration, measure Adam, loss MSE, metric MAE, and train for 200 epoch, batch size of 64. Then we have model performance and evaluation, rated on test data, inverse transforming and P.dot against PM1. Achieve low RMSE and MAE, effective in predicting prices across varying car types, user interaction and employment potential, selective user input, brand knowledge, fuel transmission, real-time price estimation, car valuation tool, dealership type. And then for the key takeaway of this is the strong integration of processing, feature engineering, deep learning and architecture. As a result, we have accurate, scalable and user-friendly ML application. That's it from me, thank you.
Okay, next I will present a form of which is data analysis and learning model study output. First is data preparation. For data set, we use European car market data for figure. Missing value remove using df.nd. For feature engineering, we use data card age equal to 2025 minus year. The target variable was msrp.transform np.1p to enter string. For the processing step, we use numerical features to scale, which is to scale with standard scale. Categorical features, we use encoded with one encoder and we use column transfer for consistency. For model architecture, we use reverse sequential. We use this layer, which is 512 to 56 to 128. We use window activation, L2 regulation, we use activation, L2 regularization to up and batch normalization. For upper layer, we use 1 as a linear activation. For training setup, the loss will be mean square error, the metric will be mean absolute error, the optimizer is Adam, which is learning rate equal to 0.005 to 0.005, and for early stopping, we use patient equal to 20 to restore base weight. Next is explanation on finding figure and result. For the evaluation metric value on the set, we get MAE 5567.88, which is average ability prediction and actual MSRP. For MSE, we get 3280.19, which is indicate higher penalty for less error. For the cost curve, training and validation loss of inputs, the graph illustrates that for training and validation loss measured in mean square error slightly high but decrease sharply in the value post, indicating rapid learning. As training progress, the losses continue to decline and stabilize at low values, showing that the model effectively minimizes error. The close alignment between the two curves throughout the training process suggests that consistent performance of both training and validation data, indicating good generalization and no overfitting. Overall, the model demonstrates stable and efficient training with strong predictive performance. Next, graph for training and validation MAE over inputs. The graph shows that for training and validation mean absolute error MAE is quite high, indicating less prediction error, but decrease sharply within the first 35 inputs, reflecting rapid initial learning. As training continues, the validation MAE stabilizes at a low value, while the training MAE gradually decreases and remains slightly higher. This pattern suggests that the model maintains consistent performance on unseen data, generalizes well and does not overfit, demonstrating effective and stable learning throughout the training process. Next is graph for actual versus predicted MSRP. The graph presents a scatter plot comparing predicted and actual MSRP value, with the weighted line indicating perfect prediction. Most data points are closely aligned with this line, demonstrating the model high accuracy. While slight under prediction appear for higher price per vehicle. Overall, the model performs well across the data set. The tag specific along the perfect line suggests that the model effectively captures the underlying pattern in the data, makes strong predictive performance and minimal errors. Next is residual plot predicted versus scaling graph. The residual plot illustrates the difference between actual and predicted car price, with most residual clustered near the residual line, indicating good model performance for lower to mid price vehicle. However, as predicted MSRP increase, the residual become more displays, revealing reduced accuracy for high-price car and suggesting heterogeneity. The presence of a few large outliers further indicate that the model significantly mispredict some vehicle, likely due to limited data, missing details, or model limitation. Overall, the model predict well for most cases but need refinement to better handle high-value prediction. Next is regard of distribution of original MSRP. This model revealed a highly widespread distribution of MSRP values, with most car priced below 100,000 and a test concentration between 20,000 and 40,000. Along that extent toward the high price exceeding 1 million for a pure limited or exotic vehicle. This embedded in the data likely contribute to the model performance on high price car as it and better will result in the average range value. Addressing this due to the need of lot information, sampling or stratified training will help improve the model accuracy, particularly for expensive vehicles. And lastly, the graph of distribution of block transform MSRP. The histogram of the block transform MSRP show a more balanced and symmetrical distribution compared to the original split data. This information helps the training model fit across range more equally, improving training stability and accuracy. By reducing the impact of extremely high price, the model can better learn pattern across both low and high price vehicles, leading to improve generalization and prediction performance.
Through the data for pre-processing, feature engineering, and model training, the project showcases how deep learning can enhance prediction accuracy in the automotive domain. The diversity and detail within the dataset enable the model to generalize well across a wide range of car types and configurations. The successful implementation of this predictive model highlights the potential of AI-driven tools in assisting buyers, manufacturers, and dealers in making data-informed decisions. It also sets the foundation for more advanced applications such as real-time car valuation systems, personalized recommendation engines, or market trend forecasting using similar techniques. That's all for our group.
Next, we will do Q&A section. For the question is, what technique was used in the car price prediction system to handle the skewed distribution of car prices, MSRP, and why was it important? Thank you.
Answer the question from Shahid. I think the car prediction system applied a log of transformation to the MSRP target driver to handle its highly skewed distribution. This was important because the original MSRP values had a long right tail due to extremely high price vehicles. Such skewness could cause the model to bias toward predicting low prices and be overly influenced by a few expensive outliers. The transformation made the distribution more asymmetrical and normalized, which improved the model's training stability and allowed it to learn more effectively across both low and high price vehicles. That's all. Thank you.